Good morning all. Today we're going to use the 2N3904 NPN transistor to turn on a 24 volt relay. Now here's the switch. I'm going to have 5 volts applied to this switch, and here we have a current limiting resistor going to the base of this 2N3904. So when I push this switch, this relay will be turned on by this transistor. The contacts of the relay will be indicated closed by this LED. I have 24 volts through a current limiting resistor going to the anode of the LED. The cathode of the LED is applied to the contacts of this relay. Now the other side of the contact goes to ground. Now here I have 24 volts DC to power up the relay. Here's ground. Over here is 5 volts into the switch, which will be applied to the base of the 2N3904. The emitter of the 2N3904 is going to ground. Both the 5 volt and 24 volt power supplies share the same ground. The collector of the 2N3904 transistor is going to the coil of the relay. The other side of the coil is going to plus 24. When the transistor is turned on, the relay is connected to ground through the collector base emitter junction. Now let me push the switch and we'll see what happens. There we go, look. We've driven the transistor into saturation. That applies the relay coil to ground. The contact of the relay coil closes and current flows through the current limiting resistor, through the anode cathode junction of the LED, through the relay contacts, and back to ground. That is amazing. Let's see what the voltage across the collector emitter is when we turn that transistor on. I got my Fluke DMM set to volts. We're going to measure the voltage across the collector emitter junction of the 2N3904 transistor. Now right now, with the transistor turned off, I have 22.88 volts across that collector emitter. Now I'm going to push the switch and apply the 5 volts to the base of that transistor, and we'll see how far into saturation we go. Look at that. We have 0.168 volts across that collector emitter. Nice. Off, 22.87. On, 0.167. 167 millivolts. Off, on. Isn't that amazing? So when the transistor's turned on, we have in effect 0 volts across that collector emitter, and all of the voltage applied across the coil of that relay. where we go. Now when we get to the house, I'll discuss this circuit right here. I'll show you how to calculate the base resistance and how to calculate the current limiting resistance of this LED circuit right here. We'll see you when we get there. Hello, here we're at the house, and we're going to talk about this circuit right here. This is a very nice circuit. We use a 2N3904 NPN transistor used as a switch, an on-off switch, to turn on this 24-volt relay. When I press switch S1 right here, 5 volts is applied to the base emitter junction right here. We have current flows through this 16 kilo ohm resistor into the base emitter junction. And when that occurs, we have current flows from the 24 volt DC power supply through the relay coil, through the collector emitter of the 2N3904 back to ground. When current flows through this coil, this contact closes and connects this 24 volt DC power supply to ground through the current limiting resistor. We have current flows through the current limiting resistor of 1.2 kilo ohms, the anode cathode junction of the green LED, and to ground, because we've closed this switch by energizing that relay by turning on that 2N3904 when we closed S1. Now all of the grounds are common. So the ground of the 24 volt DC power supply here and here are common with the separate power supply of plus 5 volts DC that drives into the base of that 2N3904 resistor when we close this S1 switch. Now, people, what's the purpose of this 100k ohm resistor down here? We know that current flows into the base emitter junction through the 16 kilo ohm resistor, but what is this guy doing down here? Well, when I open up that S1 resistor, when it's not pressed, I want to ensure that this transistor is not turned on. And so, we open up that switch right there. It's not pressed. We have a floating gate if this resistor is not here. What this resistor does, it ensures that the base of that 2N3904 is not floating. It is pulled to ground right here through that 100 kilo ohm resistor. Well, there you go. Isn't that amazing? Now, the amazing part is coming up next. I'm going to show you how to calculate this resistor and this resistor. Hold on, we'll get there. Hello all. Now we're going to take on the easy part first. And that's calculating our LED. We want a current limit the current through this LED so we don't burn it up. Now here's the formula. I'm going to turn on my calculator. Here's the formula. Our LED equals VS minus VLED divided by current LED. Here's VS, we're using 24 volts DC. Here's VLED, the green LED, and we want the current to flow through our LED, which is VS minus VLED, the voltage across our LED, through the current flowing through this circuit right here, the green LED, to ground. Now here is the contact inside relay 1, that relay that we are energizing by turning on the 2N3904 NPN transistor. I don't have that circuit drawn in here. That'd get too convoluted with all of this, this circuitry right here. So I just have the source voltage, the resistance, the LED, the relay contact, and ground. VS and ground. So what do we do here? Well, we have this formula right here. Our LED equals this voltage. Don't turn off. Don't turn off. Calculator, stay on. Our LED equals this voltage minus this voltage divided by the current in that circuit. Oh, come back here, pencil. I got jammed up against the music stand. So here we have 24 volts minus the voltage across that green LED divided by 20 milliamps through that circuit right there. And that gives us a resistance right up here, 1,130 ohms, 1.13 kilo ohms. The closest value to our calculated value is 1.2 kilo ohms. Let's put this into the calculator here. We have, let's parentheses, 24 volts minus 1.4 close parentheses divided by 20 milliamps. And there's our resistance, 1.13 kilo ohms. Isn't that easy? Now, if this was not a perfect switch, we would have to add the voltage drop across that switch into our calculation. But we always assume that switches, when they're closed, we have 0 ohms across that switch. The perfect switch. So, with a 1.2 kilo ohm resistor, we are limiting that current to 20 milliamps. You pull up the data sheet on that green LED and it says that we want to have 20 milliamps flowing through that anode cathode junction. Alright, in just a hair we're going to talk about how to calculate the base resistance into that 2N3904 NPN transistor to turn on that 24 volt relay coil. Hang on, folks, it might get a little bit dark. Here we are late in the afternoon, but we'll try to get there. My calculator keeps wanting to go into standby mode. Stay up, calculator. Don't go to sleep. Alright, folks. Alright, we'll see you in just a hair. Here we are, day 3 of this video. And we're going to figure out how to energize this relay coil, pull the contact closed. I don't show the contact, but here's the relay. And we saw the contact in the last segment of this video. Here, the 2N3904, when turned on, is going to allow current from the 24 volt DC power supply to flow through relay 1, that relay coil, through the collector emitter junction back to ground and energize that relay. But in order to do so, we have to do some calculating. And this is where it gets a little bit hairy. Unlike the figuring out the LED resistance in the last circuit we had looked at, this one right here takes a little bit of effort. So you pull out your electronic slide rule and we'll be able to do it. It's not that hard. It's not that hard at all. But let's go back to the circuit and let's see what's going on. Here we have plus 5 volt DC applied to the base emitter junction, and when that is done, current flows through the coil to ground of that 24 volt DC power supply and ground. All grounds are shared, the 5 volt DC ground and the 24 volt DC ground. They're all shared. Now let's get on with it. Up here is a parameter called HFE, and sometimes you'll hear it as the beta parameter. That's the transistor gain. And it is defined by HFE equals current collector divided by current base. Now current base is equal to current collector divided by HFE. Now here is the current collector right here. Current base is equal to 17.79 milliamps divided by HFE. Now HFE for the 2N3904 is the value of 70. Now where did you come up with this 17.79 milliamps for current collector? I did that down here. We have 24 volts divided by 1.349 kilo ohms. That is the coil resistance of that relay. Current coil equals 17.79 milliamps, and current coil equals current collector. So here, 24 volts divided by the resistance of the coil, 1.349 kilo ohms, equals current coil, 17.79 milliamps. That's this value up here. Let's turn on a calculator, because we're going to figure out what the base current is to allow 17.79 milliamps to flow through that relay. Let's clear out our calculator. We're going to go 17.79 milliamps divided by HFE beta 70. And that gives us a base current of 754.13 microamps. It is tiny. Okay, so let's clear that out. So here, resistance base is equal to 5 volts minus 0.7. That's 5 volts here, and 0.7 across the base emitter junction of the 2N3904 divided by this value up here, current base, 254.16 microamps. And we come up with a base resistance of 16.92 right there. Now the closest value of our base is 16 kilo ohms, and that will drive that transistor into saturation and allow current flow through the relay coil back to ground and turning on, energizing that relay. Isn't that amazing? We did it. Okay, so a couple of things, and I want to reiterate here. When this switch is open, the base is floating unless we pull down to ground through this 100 k ohm resistor. Another thing that you have to put in here is this spike suppression diode. If you don't have that diode in there, when the magnetic field collapses, when you turn this relay off by opening up that switch, the magnetic field collapses and it generates a huge voltage. And that huge voltage will damage that 2N3904. So you have to put this reverse biased diode in here. Cathode up to 24, anode to the collector. And when that magnetic field collapses, all of that huge energy is remained in this coil to the forward biased diode until that magnetic field is dissipated, protecting that 2N3904 transistor. Well, did I miss something? I probably did, but y'all figure it out from my drawings and calculations. All right. Okay. Whew. Man, I get long-winded every now and then when I'm trying to explain this stuff out. Ignore me and just look at the numbers. You'll be all right. All right, folks. Good night. We'll see you when the sun comes up.